welcome back to this afternoon session. It's a pleasure to welcome back Professor Fabien Pazuki, who will give a second lecture. All yours, Fabien.
Hello, everyone. It's a pleasure to see you again. So we meet again today for the second part of the lecture on the modular curve x naught of n. So yesterday we arrived at this slide where we defined the height of algebraic numbers, and we mentioned that this object satisfies a Northcott property, which means boundedness implies finiteness if you bound the right parameters. And then I also mentioned that the algebraic number of height 0 are precisely the roots of unity, and of course the number is 0. So now we move up in the game, and we're going to talk about heights of geometric objects. But let me start by projective points. So let's get to this together. So we have a projective point in the projective space of dimension n. It has n plus 1 coordinates. There are algebraic numbers. We define its Weyl height, sometimes called projective height, by this big formula that, of course, looks a lot like the previous one. So we are already used to the places, the degree of a field that contains the elements where we take the absolute values. All these absolute values come from the places, and we take a max. So we take the sum over all absolute values, and we take at each place the max of the v-adic absolute value of all the coordinates that we have here. This is well defined. It's a projective point, so there's at least one coordinate that is non-zero. That's by definition. So this makes sense. And then that's the height that we have. Same as before, extension formula and product formula ensure that this is well defined. So we have an object that will now measure the complexity of our projective point. So now this height satisfies also a Northcott property, very similar to the previous one. So if you bound the height from above, and if you bound this QPQ, this is the degree of a minimal extension of Q that has all these coordinates rational. Yeah. So if you have that, then you get the Northcott property. So you need to kind of maybe normalize slightly here. So I assume, for instance, that one coordinate is 1. You can just divide by x0 if x0 is not 0, and then you normalize by the first coordinate being 1. That's also always possible. The height will not change because of the product formula. So that's one of the nice perks of this formula. So of course, the formula is very similar, and indeed, in fact, the height, the Weyl height of an algebraic number from the previous slide is actually just a particular case of this more general projective height. It's just the height of the point 1 alpha. You remember we had the max 1 and alpha. Well, you can take 1 alpha as a projective point in P1. It has 2 coordinates, and then it's exactly the same formula. So this is not by accident, of course. So there we go. At that stage, we can measure the complexity of a point in the projective space. Now, so what we have in mind, I recall from yesterday, what we have in mind is we try to compute heights of objects that are curves or moduli spaces or families of moduli spaces. So we need to advance a little bit. Points are not enough. So what do we do now if we have a variety, projective variety? Can we, I mean, is there some kind of way to define a height? So the answer is yes. There are actually several ways. So let me start with a very naive idea. So now I move to projective varieties. I mean, you normally restrict to reducible, and then if you have several components, you add up. So, or you take a max or something. So I'm in the irreducible projective setting. X is my variety, and let's imagine it's really given by some complete intersection. You really have some polynomials, explicit polynomials in n plus 1 variables. I have, say, R of these polynomials, and then I'm looking at the systems, the system, vanishing system defining this X. Let's imagine that X is given like this. So one way to do, as we have some experience with heights for easier objects, so like points or numbers or maybe, I mean polynomials. A polynomial in a way is given by the data of its coefficients. So basically what we could do is we construct a point in some big projective space such that the coordinate of that point would be the coefficients of, say, f1 first, and then f2, and then until fr. So we take all the coefficients of all the polynomials defining this x, and now we have these polynomials, they are homogeneous. And now we have a big vector in a way, and we can take the height in the previous sense. So you see, we can use what we've developed for easier objects to now try to define a height for something slightly more complicated, as long as we have a bit of data as given at the beginning. So okay, this is possible. Of course, it's very simple, and it's rather easy to implement in practice. So imagine if your task is to actually compute explicit things on your variety x, and you want to use a computer for this, you kind of need to explain x to the computer, to the algorithm, if you want to perform some algorithms or something. So in that case, most likely you will start by something like that. If you have the fi given, you program the whole thing like this. So it's actually easy to implement. Your equations are given, fine. However, of course, if you know a bit of geometry, you realize that it relies on many choices. If the data is just, if you just consider geometrically a projective variety, first you need to choose a class of embeddings if you want. I mean, here I give you already some polynomials, but in real life, if you do some arithmetic geometry, sometimes the variety does not come up directly with equations. Sometimes it's just coming from an induction process that you're doing, some intersection that you're doing in a bigger space or something. So it might not be given with all the choices made for you. So you might actually need to make the choice of the projective embedding and then the specific sections that you need to use. So there's a lot of choices, and for some, I mean, in some applications, this is considered kind of bad. You try to avoid to have choices so that your result is more canonical. I mean, this is of course a natural instinct we have. So here you see the tension is between having something very simple that you can compute easily and having something very canonical, very intrinsic to the object that you study. So there are ways that are more to compute the height or to define a height of algebraic geometric objects that are more intrinsic. However, they rely on a bit more theory. So we will see some of it. And it's clear that then comparison theorems will be important. So, I mean, this is a perfectly fine height for some problems to solve, but then other problems need something more intrinsic. And then sometimes you kind of need results from both sides, and it's then important to have comparison theorems for the various heights that you define. So in the sequel, I decided to present two important situations that are, of course, the ones relevant to our topic. So that's when X is an abelian variety. So the abelian varieties are projective, so they fit in this game. And then when X is a curve, a projective curve. So why is that relevant? Well, I mean, the moduli space we study X naught of n is a curve, so fine. And then very often, as you will see, we have access to information about the modular curve by taking first some steps to understand its Jacobian. So to each curve, we can construct an abelian variety naturally associated with, which is called the Jacobian. It's an abelian variety that has dimension equal to the genus of the curve. So in our situation, the genus grows, as we've seen, at least linearly in n, and that's kind of big because it means the Jacobian variety that is associated is growing in dimension also with n. So anyway, knowing the theory of heights on abelian varieties will be useful to understand the modular curve. Okay, so on abelian varieties, I would like to define two extra heights. So, I mean, we already have one from the previous slide. I mean, it's a projective variety. If you're given equations defining your abelian variety, you can take the height of that equation. That's a bit naive, so we're gonna move up. We still stay in the projective setting. I mean, using projective heights in this first attempt, but it is a clever move that uses Mumford's theory. So, okay, let me fix a little bit of notation. K is the number field. I take an abelian variety of dimension G over K. I'm going to fix little r. Sometimes it's referred to as a level or theta structure level. So this abelian variety has a neutral element. It has a projective algebraic group structure. So there's a neutral. I'm going to call it 0a, for instance. And then there exists a way to choose a class of embeddings for abelian varieties that send the variety inside a projective space of a dimension that is linked with the level that you choose. So the level that you choose essentially is a torsion level. I mean, pick 2, for instance. So then basically the section that you choose to define an embedding of the variety comes from theta functions. So this is why it's called the theta embedding. So over the complex numbers, these are really the theta functions that you know. So I mean, it's actually a rather beautiful theory here. So I say in the Mumford sense, of course, Mumford contributed a lot on the series of paper on equation defining abelian varieties to this, building up on what we knew about theta functions before, back from Jacobi and so on. So anyways, there's a way to embed A inside a projective space. R plays the role of choosing how many sections you want to take linked with the torsion levels that you choose. So now the point theta of 0 by construction, it's a projective point. And then because it's a projective point, we can take a look at what's its height is. So basically the whole idea of the theta height is to say, let's define the height of A by just taking the height of theta of 0. And it's actually, maybe if you've never seen that, it might be a bit surprising because I mean, A is richer than its neutral element. And you maybe also, if you played a bit with canonical heights on model Veil groups and these kind of situations, very often the height of 0 is 0 or is trivial in some ways. It is not the case here, not at all. We didn't take any canonical height here. It's just really the height of the coordinates that are described that are given to describe the point, the neutral element, the point on the abelian variety. So now to understand that, I mean, you need to prove that it actually makes sense, that it's a useful height in a way. I mean, that it's a moduli first, that with this you can recover the variety. It's not completely obvious, but it is, I mean, in essence, part of the interest of this series of paper of Mumford is this. It means that basically you can recover equations defining the whole abelian variety just by knowledge of the theta 0. So you can actually cook up some equations where the coefficients only contain the information coming from these sections. This is very interesting. So anyways, so this is a traditional way to attack problems in Diophantine geometry with abelian varieties, is to use this theta height. It's very explicit. It's only one point that you care about, and you need to know things about these sections, these theta functions. Yeah. Of course, the whole game here is also algebraic. So there's the genius in the development of these theta coordinates by Mumford is really to explain that the theta functions, which are really complex theoretic, are actually have counterparts that are algebraic. So I mean, this is not obvious, but it's what's behind the interest of this height. Okay, so this is also a Weyl height, and as such, it still depends on some choices, but at least there is an interesting theory that tells us that this choice is has some power in a way. We can use it to do some things. It still depends on the class of theta embeddings. Yeah. Okay, so that's a classical way to measure the size of an abelian variety. But there's another way, and this is the famous Faltings-height of an abelian variety, where really we try to remove all projective embedding choice. Yeah, that's the game here. So let me go through it. It will most likely be useful also for other conversations you might have during the week. So K a number field, okay, it's ring of integers. Now we go for an abelian variety of dimension G, and instead of looking at equations defining this variety in a projective space, we're gonna focus on its Néron model. So there's a scheme over spec OK that has the generic fiber being the abelian variety you start with, and that satisfies the Néron property. I mean, it is a beautiful construction. This is a classical construction as well. This Néron model has a neutral section. Yeah, from S you can go up and target the neutral element at each fiber. That's the neutral section. So what we're going to do is we're going to focus on the space of G differential forms on the scheme. And what we're going to do here is take the pullback of this space through the section to get something well defined on S. Okay, so what is this move? This move is trying to avoid choices. We follow trying to give you maybe a bit of intuition if you're not used to playing with vector bundles here, the line bundle. I took the determinant. What we try to do is so we look at differentials because we understand that they know intrinsic things about the variety. And then we take a look at the determinant of what the differential forms generate as a vector space. And the determinant here, I mean, the determinant of the base is will give you some volume. Now, this volume, as often when you take a determinant, will be independent of the choice of the base. That's a little bit behind the idea here. Yeah. So okay, well, we defined now a line bundle over spec OK by just pulling back this interesting line bundle over A. That's the tradition. So this is the first part of this slide. We try to focus on something that is intrinsic to the abelian variety. Now, the second part of this slide is if you give me any line bundle over spec OK, and if I'm allowed to pick a non-zero section S of L, then I would like to do two things. I would like to compute the degree of L over S OK. So L is a line bundle. It's something of dimension 1 over OK. So I would like to compute this, L over S OK. S is non-zero. This will be finite. Yeah, it's a bit like some Z over NZ if you want, or I mean, I have something of dimension 1 and over OK. I just take a look at what the section knows about L in some way. So I quotient here, and this is a finite quotient. That's the one thing I want to do. But there's another thing I want to do at each Archimedean place. I also want to measure the size of S. So from now on, taking degrees will be a little bit more than just taking a classical quotient like that. We also focus on how to metrize the line bundle, and by the choice of some specific metrics, we will define what is called the Arakelov degree of the metrized L. So which is just a classical degree in a way, but then you add a term that is coming as minus log of this metric. That is the choice you made on the Archimedean side. Okay, so we have a very specific line bundle coming from the Nero model. And now I'm telling you for each line bundle on spec OK, if you can come up with a nice metric, then you can take an Arakelov degree. So the Faltings-Height is precisely combining these two ideas. For any L, we can compute the Arakelov degree. We have a specific line bundle that we're interested in. Let's take the Arakelov degree of that line bundle. That's what the Faltings-Height does. So here's the definition. So this is the line bundle. However, as you've seen before, we need to metrize. So we need to define some metric to measure the size of sections. So the metric that is taken is a rather natural one, L2 metric. So here it is. So S is identified with a wedge product with dimension G of elements of the differential forms, because this is the line bundle we look at. And then we wedge again against S bar, which means we reach dimension 2G, and that's the complex torus we face. So this is now a volume form, and the whole integral has a meaning, and it gives you a number. I took the absolute value here, so because there's a power of I if you want when you play with the wedge. So this is actually a positive or a non-negative, well, it's positive number. So this makes sense to call it S squared, and it actually really defines a metric that has very nice properties. That's the metric we place at each Archimedean place, and now we have a way to define the Faltings-Height in this Arakelov degree form. So since the beginning, I'm telling you we want something intrinsic that does not depend on choices, etc., etc. And now what do? I choose some metrics. So, okay, sure, yes. However, it does not depend on projective models. We did not use equations to define the abelian variety. That's what we wanted to avoid. Instead, we use differentials. And then it does not depend on the choice of the non-zero section S. And that's very important. As you can see from the notation, there's no mention of little s. However, in the definition, of course, you use a little s, yeah, so which is how to define the metric here, for instance. So this needs a proof, of course, and to prove this, well, first you need to see what kind of ambiguity you have on S. The only thing you can do to S is multiply by some element. I mean, this is a dimension 1 object, so if you multiply by one element, the formula, the general formula defining the Faltings-Height or the Arakelov degree will be independent of this choice because of the product formula on your base field, which is a number field. That's a global field. So the product formula is valid. So that's how it goes. So now we have an object. This is a real number. Note, it's not completely clear that this number is non-negative. And why is that? Let me just go back for a second. You see, you take minus log of the section, of the norm of the section. This is of course non-negative. I mean, this is an integer, but here it's a little bit less clear because you have a minus. So if this is big, then actually this can be negative too. And indeed, it happens with this normalization. This is the Faltings normalization. Sometimes the Faltings-Height is negative. It happens like numerically if you compute it. But it's bounded from below, so which is necessary for a height if you want a Northcott property. Okay, talking about Northcott property, it's a fact that the Faltings-Height actually satisfies a Northcott property. What does it mean? It means that boundedness implies finiteness. Now, because the situation is slightly more difficult than just algebraic numbers, you have to be a bit careful with that statement. You kind of need to know what kind of finiteness you get if you bound the Faltings-Height from above. And so you need to fix the base field, you need to fix the dimension. It's up to isomorphisms. I mean, there are, of course, there's a clean statement. So, but it satisfies a Northcott property. And this property actually plays a crucial role among other techniques in the proof of the Mordell conjecture. So this is really the height that he's using to prove the finiteness of rational points on the curves of genus bigger or equal to 2. So I decided for two things now. I would like to give you a little bit of intuition if you've never played with Faltings-Height by computing it or giving you the formula for elliptic curves in dimension 1. An elliptic curve is an abelian variety, so suddenly we have a new theory to compute its height as a curve. So then we can take a look at this. So that's the next slide, and then after that, I'll explain the strategy to actually prove the Faltings-Height satisfies a finiteness property. And this will be based on some comparison result. So I think it's also important to see how comparison theorems can help you getting where you want to go. Okay, so first step, what's this Faltings-Height for an elliptic curve? Elliptic curve, dimension 1 abelian variety. Let's imagine your curve is given in a short Weierstrass model. So here again, I choose a model. Why do I do that? You don't need to do that to use the Faltings-Height for elliptic curves. I'm just doing that to show you how it relates to invariants that you're maybe more accustomed to if you don't play with the Faltings-Height in general. So this slide does not imply that you need a Weierstrass model to compute the Faltings-Height. Not at all. You don't need. You just use the Néron model. However, if you have a Weierstrass model, if someone is playing with an elliptic curve using this model, then you can still help that person by computing the Faltings-Height following this line of thinking. So what are we doing here? We have an explicit model. Of course, it's an affine model, but you can, I mean, the difference between affine and projective for elliptic curves is easy. So I keep on with the notation in the affine form. So now there is a section, you remember there's a section to choose a non-zero section where you can compute the metric and you can compute the Arkelov degree using this section. We know the theory tells us the result does not depend on the section. However, if you want an explicit result, you kind of need to choose one. Let me choose this one. So I don't choose this one for nothing. So delta A is the minimal discriminant. And dx over y is essentially the only non-trivial differential you have on this curve. Yeah. So this is not too hard to prove. So now dx over y, if you play a bit with you want something intrinsic. So you're aiming for, I'm explaining the choice of this section. So you're aiming for something as intrinsic as possible. In particular, you try to get something that is invariant under the isomorphisms of the curve. So this section is chosen in that form. So you see, this is extra. If you're not forced to put this delta in the game, but if you put it, suddenly the section is invariant by isomorphism. So the formula most likely will be cleaner in a way in the end. Anyway, so now we compute. So the finite part is not too hard to compute. You get some log of the norm of the discriminant. That's coming from the traditional degree, if you want. And then you have the Archimedean part, and that's fun. I mean, basically, it means that there's a way to compute the integral of S wedge S bar, and it should give you some kind of volume form. So the delta is really the delta it's now the modular form delta. So there's a formula linking the modular form delta with the minimal discriminant that is used in the proof, and then the im tau that you get here. To the 6, it's to the 6, but over 12, of course. It means it's a square root of im tau, but square root of im tau is essentially the determinants, the co-volume of the lattice you look at. So that's really the measure that comes from the integral. So that it's you recover this as a formula. So now we have a closed formula in dimension 1, and I would like to evaluate a little bit what this tells us. So, I mean, we're happy to see the discriminant because the discriminant tells us something useful. Discriminant tells us where the curve, the elliptic curve, is singular. Yeah. If what are the bad primes? So this is actually something we care about for in various situations. So we're rather glad to see this. This maybe, I mean, maybe we're glad too. I don't know. This is also, these are also nice functions, but maybe it doesn't tell us right away precise information about the curve. So you can work out a little bit the size of that term. So you see um, the J invariant of the curve has over the complex numbers, let's say, has a Q series. So you can expand, it has a Fourier series, yeah? So you can expand the J invariant as 1 over Q plus 745 plus, so what is that? 196,884 Q plus, and then I don't know. So you have some Fourier coefficients that are actually integers. So you can take a look at what's the size of estimate of this J invariant for the v-adic absolute value, V being Archimedean. So what's the main term in this sequence? It's the first one. Main term in this sequence is 1 over Q. The absolute value of 1 over Q is the main term in the whole Fourier series, defining, or I mean, giving you the expansion for J. And the size of log of J is then close up to something that we can compute explicitly to log of the main term. But the main term is 1 over absolute value of Q. So now absolute value of Q is exponential minus 2 pi m tau. This is easy to compute. So the inverse will give you a plus m tau. So basically log J is m tau. Now delta as a modular form also has a Q expansion. It starts with Q. Yeah. So this is actually minus log Q is the same as log 1 over Q. So these two, they must be close to each other. And they are indeed. We can prove that explicitly. So which means basically this term up to a small term, this is log of m tau, yeah, but log of delta gives you something like log J, and log J is essentially m tau, which means basically we have that the Faltings-Height in this big formula is something like the bad primes and the size of the J invariant, which encodes the isomorphic class, the isomorphism class in the moduli space. So you see now what the Faltings-Height is measuring here for an elliptic curve is the crucial things. Yeah, it's really what is the isomorphism class, and then what is the arithmetic of the bad primes over the base field where you look at it. So that's I think it's nice to see that, because it will, I mean, in the higher dimension we don't have easy invariants like this. However, we do have the Faltings-Height, and essentially it's supposed to encode enough information as it does like for these elliptic curves. So it's actually good to have to keep that in mind. Okay, so in dimension 1 it gives us something very relevant. So so we trust that. Let's go for that in higher dimension. What can we say about this Faltings-Height? So we want to prove that it has a Northcott property. So that's the maybe minimum requirement if you really want the height to kind of carry enough meaning on your object, is that you really have this crucial property that boundedness implies finiteness. Now, if you just look at the definition of the Faltings-Height, this is not obvious. It's so you need some work, and that's what Falting does in part of his paper on the model conjecture. He proves that this height has a Northcott property, and here's the strategy. So the strategy is to compare the Faltings-Height, so the king object you want to keep for later in the proof. You compare it with another height function. So for instance, the theta height, because I introduced it, but it can be any reasonable height on the moduli space of the principally polarized abelian varieties that you look at. And then, of course, you compare it to a height function where you know you have the Northcott property. Yeah. So most of the projective heights, basic veil heights, theta height, things like this, they satisfy the Northcott property for easier reasons. because it all comes back to the original Northcott property on numbers and on points on projective spaces. So the idea of the strategy here is to say, okay, this vaulting site is of a different nature. It's more intrinsic. However, to prove Northcott, we kind of need to compare it. And that's what is done. So typically, the kind of comparison you get is of the following shape. It's controlled in some kind of, I mean, this is bounded, so this must be bounded. You have no choice. But now, if the theta height is bounded, you get finiteness. You know that from previous studies. So there you go. You reach the conclusion because you have this comparison of heights. Yeah. So height comparison, it might look a bit ugly if you don't like inequalities. It's full of inequalities with constants up to bounded amounts, etc., etc. Yes, indeed, the theory is full of that. However, it's very powerful. It's if you have such control, then it means that boundedness implies finiteness on this height because it does on this height. So that's what we were aiming for. So that's the strategy to prove that the vaulting site has a Northcott property. So from now on, it means it really can compete with any other heights because it satisfies the key property. And so it means maybe we should use this one because it's independent of the various choices for equations. So that's a little bit what the community did. In fact, a lot of people moved away from the theta height to work with the vaulting site as soon as such results, not only this one, but such results were known, because the vaulting site satisfies also very nice and canonical properties with respect to isogeny classes, with respect to products, to quotients, there's all kinds of things you can do with the vaulting site that are way more difficult to achieve with this one. So of course, we moved up in abstraction. You need the Néron model. You need to understand how this is built, but we gain in power. We can do more things cleaner with the vaulting site. Okay, so now we know how to measure the size of abelian varieties. We know how to do that in several ways, and we know how to compare the results of these several height theories in a way. Good. However, our work will involve abelian varieties because they will involve Jacobians, but we also kind of need to see what we could do on a curve on its own. Yeah, maybe there are other ideas to actually study curves instead of going and building this very complicated abelian variety of dimension equal to the genus. Maybe we can just focus on the curve and actually work internally in some ways. So that's the idea if you do auto-intersection. So of the relative dualizing sheaf. So what is this idea? It's a different idea. Now X is a curve, let's say over Q, geometrically reducible, it's smooth, and we give ourselves a model of X. So now we are away from projective space. We don't want to have like a projective embedding and stuff. However, we do use a model of the curve, and it is not an easy model to cook up. It depends on the type of curve, but it exists, and it's nicely done if you want. It's minimal, so you do not have too much redundancy in the way to build the scheme. Okay, this is a bit vague, but basically there is a theory of you're going to take a look at the cotangent bundle on this. So that what does it mean? Essentially, it's very close to the idea that is developed for the vaulting height. It stems from the same intuition. You go to the differentials. Yeah, so you take a look at what's happening on the cotangent bundle, and then this bundle can be endowed with a canonical Hermitian metric. Actually, we've seen a metric of that shape. This is, you remember this integral with S wedge S bar. So it's very close to the ideas that were used to cook up the Arkelov degree, in fact. Yeah, You can do that on the regular minimal integral model of X. And now you have the Arakhelov canonical sheaf, very close to what we've done. Now there exists an Arakhelov pairing taking sheaves here as parameters, if you are as variables. And now it consists in two parts. So you can intersect by intersecting divisors. If you can describe your sheaf in terms of divisors, then you have some kind of geometric finite intersection. So for instance, you take a look at the bad primes. Typically, you want to have this kind of information. And then there's an analytic way of intersecting using Green's functions. Or admissible metrics, we call them, on the Riemann surface that is underlying the place at infinity. So your curve X has some complex points. You take a look at these complex points. The curve is defined over Q, so you can of course look at it over C. And then there's a theory of Green's functions, and then you can take a look at what an intersection can be cooked up at the analytic on the analytic side. So basically, the intersection, Arakhelov intersection sums the two. It's exactly like what we've done for the Faltings-Height. So now to define the size of X is basically one idea is to compute this omega square. So the auto intersection of the relative dualizing sheaf with the metrized the proper metric that is given by this Arakhelov pairing. So that's the size of X. So now, I mean, some people prefer to study curves using this because it's better accustomed to some of the theorems that are developed. And we have to take that into account. Even if you don't like these kind of models or these this approach, it is used, and it's actually also rather powerful. There's many things about the size of this that are really mind-blowing. I mean, it's very interesting. It's an interesting invariant. So we should take it into account in our approach because it's useful, at least to some colleagues. So we should take a look at what this has to say about the curve X. Yeah. So there's a way to measure the size of curves using this approach. For this, if you want an explicit result, you need the regular minimal integral model of X. Okay, so now there are we can move up in our construction and take the height of moduli spaces. I'm going to be brief here. Imagine my moduli space is itself projective. Well done. In that case, no problem, because now I have a structure that is projective given by some implicit equations. So I can define the height in various ways using previous theory, yeah, because I already know how to compute heights of objects in projective spaces. So there is a way to define the height of a moduli space that is very natural if the moduli space is projective, which means you need to compactify. You see, it looks like it's easy and quick, but it implies a lot of work. You need to choose a compactification. There's efforts. Yeah, but it is possible. So from a very theoretical perspective, from far away, if you have a moduli space, if you know it's projective, or if you can compactify it, then there's a way to measure its size as a space. Okay, fine. So now if we have a way to measure its size as a space, and if we have a family of such spaces, nothing prevents us from taking the height of each member of the family of the moduli spaces now, and suddenly we have a sequence. Yeah, so we have a sequence of moduli spaces depending on a parameter n, maybe a level of a modular curve. And then it means you have a sequence of heights. And natural question, if you have a sequence, each time you have a sequence, probably you're interested in what happens at infinity. What happens if the parameter tends to infinity? So that becomes a very natural question. Yeah. So we can deal, if the moduli spaces are projective, we can deal with heights of families of moduli spaces because we build on what we know about projective varieties. Very good. So that's where we are now. And now we can finally reach the final section. So I'm going to talk about the height of x naught of n. But now I know a lot of things. So I know x naught of n is a curve. I know it's projective. I know it has a Jacobian. So there's an abelian variety in the game. So I can actually attack this question of height with various angles. And that's what I'm going to do. Of course, I'm going to use help from colleagues. So for instance, from Jürg, let me start with this theorem. This is a theorem where we compute the Faltings of the modular curve. So now the Faltings of the modular curve is actually the Faltings of the Jacobian. So now inside this talk, I can take that as a definition. Yeah, it's basically I can decide that to measure the size of x naught of n in the Faltings way, I name it as being the height of the Jacobian. Now, if you go deeper, if you go and read about the Faltings height in general, there's a way to measure Archimedes degrees for any kind of acceptable varieties. You can actually define this independently using similar constructions with the relative the Hodge bundle of the curve. And then there is a theorem of Grothendieck that actually tells you that the two heights are equal. So the two heights in any case, they are equal. So now this height, the intrinsic height of the modular curve, what is it? Well, what we can say is that when n grows, it grows as g over 3 log n. The main term is g over 3 log n. G is the genus of this curve. But now the genus of this curve, we can compute it exactly since Shimura, or maybe even before. So the genus of this curve has an exact expression. And if you take a look at all the terms in this exact expression, I mean, you will have something a bit more precise a bit later in the slides. It's in between n and n log n in size. Yeah, we have more precise formula, but in size, it's like that. So basically, this grows at least like an n log n over 3. This is for the Faltings height of x naught of n. So there are some error terms that are controlled. And so maybe a little bit of attention here. So n is supposed to square free and coprime to 6. So there are little details on some of the levels for the modular curve that that push for this hypothesis. However, it gives you, if in a way, it's a way now it's a first answer to measure how complicated the curve is. Yeah, its Faltings height is growing to infinity with the level, with the torsion level that you fix, and it's growing at least as an n log n over 3. So this is what we know now. We understand what's the size of x naught of n from the intrinsic perspective. Yeah. So of course now, if you really want to do that explicitly, you kind of need to compute the Jacobian. You kind of need to compute quite a few things. I mean, this is not easy to get, right? So the theory behind, you had a glance at it. The theory behind is deep. So okay, keep that in mind. We have a way to decide on what the height of x naught of n is, and this gives us this in the Faltings sense. So that's the first approach. Now there are other approaches, and I would like to mention that. So in '97, so previous result, there was a way to compute the omega square for the curve x naught of n, and here you see, so same hypothesis, and it's square free and coprime with 6. When n tends to infinity, if you have, so the whole proof is on the minimal regular model of x naught of n for omega, then the omega square is 3g of n log n. From the previous slide, you know that g of n is at least n, so it grows as an n log n with a factor 3 here. Same control on the error term. So here as well, you see the omega square knows something rather intrinsic. It seems they almost agree. you see the omega square and the Faltings when n grows, they behave very similarly. Like they are in the class of n of g of n log n when you measure the size. Yeah. So I add a note here because in the recent paper, Dolce and Mercuri, they removed the square-free hypothesis here. Yeah, this still coprime to sig is still necessary, but square-free was removed. So this is really we're close to the truth. So okay, so it means now we know how to measure the size of x naught of n for the Faltings, and we know how to measure the size of x naught of n using the omega square. Good. So there's, as I hinted, and maybe some of you know already, the two are linked, omega square and Faltings. So I take one slide to mention this because it's actually a very important feature. If you have a curve with a semi-stable Jacobian, so this is not always achieved on the base field. So to get you can always find a semi-stable model, but you might need to add to extend your base field. So this okay, fine, let's do that. So curve genus G, semi-stable Jacobian, then the Faltings of the Jacobian is actually equal up to this to the omega square. And what is left in this beautiful Noether formula? We have the bad primes and some multiplicity of the bad primes. So the bad primes are here. We take the norm, and this is the multiplicity of the bad prime on the model where we compute the omega square. Then you have this very interesting invariant. Looks, I mean, it's the same delta, but it measures something slightly different. It's called the delta invariant of Faltings. This is really a complex invariant. So we have this sum over all the complex embeddings of the base field. And then we have a normalization factor that is linear in G. Yeah. So this is really a very beautiful formula. It's actually very useful in various settings. But you see, so the size of we can apply that to x naught of n as long as it's a Jacobian is semi-stable, so maybe over an extension of the base field. And then it means the height of x naught of n, so of its Jacobian, but then the height of x naught of n as well, is equal to the auto intersection, the omega square. And then there are some terms that actually carry some weight as well, and that need to be analyzed. So it's actually very interesting to have that. I do mention something on this final little term. So this will obviously move a little bit if you change the normalization of your Faltings. This is explicit, the C0 is explicit, kind of log of 2 pi or log of 2 or something like that. But basically, it is important to keep track of what's happening here if you are interested in families of Jacobians, because you see, G depends on G is the dimension of the Jacobian. It's the genus of C. So if you have a family where the genus grows, suddenly your little term that was considered an error term is also moving. So you kind of need to be careful that it's not moving too badly and that it stays in the error term. Yeah. So it's important to keep track of that. Anyway, so this is an important formula that is in link with the two first ways of measuring the size of the moduli space x naught of n, viewed as an algebraic curve. You have these two ways. Okay, so now I would like to move back to the good old modular polynomials, and I present my recent result together with Florian Breuer and Désiré Guijon-Gomez. So what we have here is another way to measure the size of the modular curve, but really coming from the very beginning of the story where we had this model, this polynomial, modular polynomial, very, very singular. So far away from any model where you can compute the omega square, far away from any model where you, in modern days, really work with algebraic curves. It's really a kind of a bad model, but anyways, we take a look at this polynomial, and then what we were able to prove is that the height of this polynomial, what is the height, is the most naive height you can dream of, is really the very first height we had from the beginning. You know, just height of rational numbers. Yeah. So you know that this polynomial has integer coefficient. You take the max of the height of the coefficient. So it's just log max of the coefficient. So it's really the easiest thing to do. And then what we can prove is that this is bounded above by 6 psi of n. So psi of n is the main term in the genus formula. So I will recall that in the next slide. So this is always between n and n log n. That's the main term, this psi of n. So we have a control between 6 psi of n log n. So that's the main term. Then we have a secondary term, which is given by that. It looks a bit complicated, but if you like analytic number theory, of course, you can get a quick glance at what can be this size. I mean, there's a p to the n, there's a p to the n minus 1 plus 2. So that's essentially 1 over p in size, if p is big. So this is essentially a log p over p. So that's the sum of log p over p that's smaller than a log n. So you know this is a smaller term. And then you have a third term. This C2 is just an explicit constant. Yeah. So that's the upper bound. Now, there were upper bounds before on this. I mean, it has been studied by several colleagues, but this is the best upper bound that is valid in general. There were good upper bounds as well by Sutherland, Booker and Sutherland on prime levels, but this is the best for general levels. And now you will see, of course, if you take a look at the lower bound, actually you cannot really beat that except if you go for a smaller C2, because you see this is the main term. It's the exact same. So the lower bound is the same size, and the second term is also the same. So it's only at the third term in the asymptotic development that there is a discrepancy between the upper bound and the lower bound. So we fought a lot on this inequalities. So now we have an inequality that is valid for any n, and that actually gives us the asymptotic up to the third term. So I mean, you have the two first terms and the asymptotic development of this height. So why is it relevant to our, well, it is relevant, it's nice because it's one way to measure the size if you want, but I want to compare it to the previous ways. So first of all, a word on the proof. To actually get the optimal bounds, we need the veil in the proof, we need the veil height of algebraic J invariants, we need the Faltings height of elliptic curves, we need to understand the variation of these heights in isogeny classes. Then we also need some isogeny estimate coming from previous work of Masser-Wüsters extended by Gaudron and Raymond. And then do not underestimate the input of OTCS papers on this game. I mean, the Hecker correspondence paper he has has been very instrumental to us. And then, of course, previous work of Paula Cohen on asymptotics of these heights. So there's quite a lot of things you need to pile up to cook up the theorem that I proposed. So I would like to compare it quickly to what we know. So you see, we have an optimal result on a naive height, but we needed more theoretical height to actually get the result. So I'm not saying naive heights are better. You need the clever heights to actually prove something on naive heights. Yeah. So how does it compare? Well, there's a comparison theorem we also have in the paper. So if now n is square free and co-prime to 6, we add that because we want to use the asymptotics that we know on these two terms. Then what we have is that actually the Faltings height of x naught of n is up to this explicit absolute constant, the height of the modular polynomial, and the same for the omega square. Omega square is also basically just up to 1 over 24, the height of the modular polynomial. That took me by surprise a little bit, because I always felt that probably this height is interesting, but not as refined. But it seems that, in fact, we have asymptotically, we actually have two theories that match, three theories of heights that match perfectly. Everything is computed, and basically, if you approach the height of x naught of n by the Falting's way, by the auto-intersection of the relative dualizing sheaf, or by the modular polynomial, even though the modular polynomial is very singular, then you actually get a similar powerful height theory at the level of families of moduli spaces. So that was an interesting outcome of this study. So I have my conclusions now, and then it will be the end of this talk. So first conclusion, the size of the modular polynomials is very clearly understood because we have this comparison with the main terms on both sides. But maybe the number one thing we should say, and of course it was already known by people who compute explicitly these things, is that the size is huge. I mean, look at this. The main term is 6 psi of n log n, so essentially is 6n log n, but the height is logarithmic. So it means the coefficients grow as exponential 6n log n. I mean, even if you take n is 2, it's big already. So I mean, if you want to do explicit families, it's gonna be difficult because the polynomials really have huge coefficients. Yeah. So this is something you should keep in mind. These polynomials, they are very big, and because we have the bound from above and from below, we know that it's not because the bound is weak. The bound is sharp, actually. So the coefficients are huge. That's a fact of life. So this is the number one conclusion. Number two is what I said before. It seems that the three theories agree. The three approaches are equivalent to compute the size of the modular curve. And that's a very good news for us because it means that basically you can use the one you like, the one that is the most approachable, or and then of course there will be a bit of work to pair it with maybe other results that come from the other side. But we've done part of it, at least asymptotically, the height theories match. So that's I think good news from the internal coherence perspective. We were glad to witness that. Yeah. So I thank you for your attention.
Are there any questions? No? If not, let's thank the speaker again.